Welcome to 8.1 Sequences and Series. Chapter 8's really an island. We could have had this the very first unit of the year, and you would be at no disadvantage. So it's kind of a clean slate, fresh start, which is good news if the past chapter or two have been tough. So good opportunity for a rebound, and really leads us into some interesting things by the end of this chapter when we get into probabilities and probability of events, of really interesting counting principles. But anyway, a sequence is really, there's a formal definition here. You're welcome to take a look through that. But it's really just a list of numbers, where we would read, instead of like A sub 1 or A1, we would think of this as the first term, second term, third term, fourth term. That's the positive integers that they're talking about there. The numbers in the sequence do not have to be positive integers. They can be fractions, or in fact you could probably have a sequence of variables. But it's just really a list of numbers. How that differs from a series is really just the sum of the elements of a sequence, or it's just series is just the sum of a list of numbers. Okay, so series is the sum, sequence is just the list. And you're going to see some things. We're going to talk about factorials, kind of, and again, you're always welcome to pause this, read through this. We're going to talk about factorials. We're going to talk about this summation notation, sigma notation. Our calculators are going to do some of the heavy lifting for us there, and different properties of these. Very straightforward once you understand what this summation is doing. And then definition series can be written in summation form. This just says the sum of all the terms from 1 to n, and that's all of our terms from 1 to n. These things are just synonymous. So some of this will be needs to know. Let's go ahead and get started. Writing the terms of a sequence, write the first 5 terms. So A1, this is probably the only time I'll do this, write this all out, is 4 times 1 minus 7, or 4 minus 7, negative 3. A2, the second term, it's just like a function. If this was A of n, we would just put 2 here, 2 there. Is 4 times 2, 8, minus 7, 1. A3 is 4 times 3, 12, minus 7, 5. A4, of course, is 4 times 4 minus 7, 16, minus 7, 9. And A5 is 4 times 5 minus 7, 20, minus 7, 13. And you probably picked up on that right away. We're just adding 4, adding 4, adding 4, adding 4. In fact, if we go back to algebra land and away from sequence and series land, and we look at this, well, our y-intercept would be negative 7. That would be like our 0th term would be negative 7. And then every time we move 1 to the right, we rise 4. So we go up a term, values go up 4. So no big deal there. So this can also be written this way. You want the first 5 terms, so this would be negative 2 to the first, negative 2 to the second, negative 2 to the third, negative 2 to the fourth, negative 2 to the fifth, or negative 2 to the first, negative 2, negative 2 to the second, positive 4, negative 8, positive 16, negative 32. And a lot of these are going to create very recognizable patterns for us. And by the time you do 2 or 3, it's like, oh yeah, I know where we're going from there. Okay, so let's go numerator, denominator, and let's not reduce. We'll save the reducing. So A1, and I could do it in this little comma form, but that's going to be when n is 1, I get 2 on 2. A2, when n is 2, I get 4 on 3. When n is 3, I get 6 on 4. When n is 4, I get 8 on 5. And when n is 5, I get 2 times 5, 10 on 6. Or my sequence becomes 1, 4 thirds, 3 halves, 8 fifths, 10 sixths, 5 thirds. And that is it. Not too bad. Okay, write the first 5 terms of a sequence using the table feature on our calculator, which is definitely a good skill to have. So I'm going to clear out of here. First off, if we're beginning with 1, we know we're counting by ones. I'm going to go into table set, second window, and I want to have my table start at 1, and this is important. Delta table is how much we're counting by. So a lot of times for algebra problems, we'd have this at like 0.01, but we want it just to be plain old 1. Let's clear that out, plain old 1, and counting by 1. So we're going to go from 1 to 2 to 3 to 4. I'm going to go into y equals, clear this guy, and I'm going to enter as a fraction. We could enter 3 to the n divided by 4 to the n. We can also use our fraction key, which we can get there through alpha y equals. And we get a fraction key here. That's the first choice. And we can do it that way. 3 to the x on 4 to the x. Not bad to get in the habit of doing that. The nice thing about that is we don't have to use parentheses around our entire numerator, around our entire denominator. Anytime we can get rid of extraneous parentheses, probably worth doing. And now, instead of graphing, we're going to go to table. Second graph is table. And we've got our values there. And they are, interesting, I've got fractions. That didn't work out. Oh, I think because I set it up as a fraction in my calculator, it actually gave it to me as fractions. That didn't happen when I went through this in class. So 3/4, 9/16, 27/64, 81 on 256. And now I just need to track down to the next one, fifth one, 243 on 1024. Okay, I think I'm going to darken this screen just a little bit so my calculator shows up better. Bear with me here. Not a whole lot, just a little bit there. Okay. Then 26, be a good time for you to try that on your own, but I'm just going to jump right back into y equals. Clear this, and we've got x times x minus 1 times x minus 2. Back to table. And it can jump back up to entry 1. A little concerning maybe that we start off 0, 0 until we look at it and say, oh yeah, when n is 1, this is 0. When n is 2, that factor is 0. So my terms are 0, 0, 6, 24, and 60. Okay, a lot of times we don't care about the first 5 terms. We just want a specific term, and that's actually easier. I just want the 5th term. I don't need the first 5. So how simple. That is just 5 squared on 2 times 5 plus 1. It's just like a function. The 5th term, 5 takes the place of n. And we get 25 on 11. And in here, 16, when a is 16, this becomes -1 to the 16 minus 1 times 16 times 16 minus 1, or -1 to the 15th times 16 times 15. This is what I refer to as a toggle switch. It's like a light switch. It's either on or off. It's either 1 or -1. In this case, 15 negatives gives me a -1 times 16 times 15. Let's see, that's 160 and 80, 240. So we get -240. Okay, so everything's going along smoothly, and now we hit these where they're going to give us some sequences, and we have to determine like a pattern and come up with a way to find the nth term. And it's pretty easy to see what's going on here. If I call this term 1, term 2, this is our term number, term 3, term 4, term 5, between every term we just add 4. And therefore, the equation of this is going to look like a line, because as x changes by 1, if we consider this x, y, or x, these x values, as x changes by 1, y goes up 3. So this is a line with slope 3, but I'm not going to treat it like algebra for right now. I'm going to say, okay, my nth term equals, we start at 3, and we add 4, 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 add 4. And an easier way of doing that, we learned back in second grade probably, was if we have to add a whole bunch of 4s together, we should use we should use like 4 times something. So this is going to be plus 4 times what? So I say, well, by the time I get to the 5th term, I haven't added 4 5 times. I've added 4 4 times. And by the time I get out here to the 100th term, I will have added 4 99 times. Because I started here. How many steps is it from the first term to the 100th? There's 100 terms here, but if I start at the first term, there's 99 steps. So how about by the time I get to the nth term out here, excuse me, to the nth term out here, I'm going to have to take not n steps, but n minus 1. And I kind of like that form for it. The back of the book might have that be 4n, let's see, 4, that's negative 4 and 3 minus 1. Now back to algebra land. What if we backed this up and found term 0? We would subtract 4 and get negative 1. And, oh yeah, we have a slope of 4 and a y-intercept of negative 1. But I really think for sequences, series, we want to think through it this way. Okay, so I'm going to list my terms up here. Term 1, term 2, term 3, term 4, term 5. This one is a little bit devilish. I notice we go up by 3, but then we go up by 5, and then we go up by 7, and then we go up by 9. And I suspect our next term we'd go up by 11 and probably get to 39 if it follows that pattern. And that is really a tough one until you have some experience with this. I'm going to write perfect squares up here. 1 squared, here's a sequence of perfect squares. 2 squared is 4, 3 squared is 9. 4 squared is 16, 5 squared is 25, 6 squared is 36. Take a look. Up 3, up 5, up 7, up 9, up 11. I don't know if you've ever noticed that before on perfect squares. The next one, up 11. The next one is 49, and that's up 13. And this pattern continues as we build this. There's a good algebraic mathematical reason for that, but right now you're going to take that one on faith. So this is like that, but take a look at the values. They're just a little bit shy. I wish this was 3 bigger. I wish this 4 was 3 bigger. I wish this 9 was 3 bigger. I wish this 16 was 3 bigger. This is an equals n squared plus 3. Let's take a look. By the time I get to the 5th term, I've got 25 plus 3, 28. So if you see that kind of increasing going on, where each time we're adding 2 more than the step before, you may be able to build this off of n squared. All right, 40, and that one, like I said, is devilish. These next ones aren't going to be as bad as that one. 46, the nth term. If we have fractions, we probably want to just look at numerators, denominators. This is term 1, 2, 3, 4, 5. Term 1, well, every term, the numerator is 1 more than the term number. Oh, so that's n plus 1. Now, the denominator, we add 2, add 2, add 2, add 2. We start at 1, and we start adding some multiple of 2. How many times to get to this 5th term did I have to add 2? 1, 2, 3, 4. How many times will I have to add 2 to get to the nth term? N minus 1. I like that answer, but we could also write this as n plus 1 on 2n. That's minus 2 plus 1 minus 1. Okay. 48. Now we're switching back and forth between positives and negatives. And something like this little toggle switch I referred to earlier, could be useful here. My numerator is times 2 times 2 times 2, and I notice this is 2 to the 0th, 2 to the 1st, 2 to the 2nd, 2 to the 3rd. So my nth term, maybe I could say, what if we made it 2 to the, that's the first term, 0, second term 1, 2 to the n minus 1. Well, that would take care of the numbers. 2 to the, when n is 1, I get 2 to the 0th 1. When n is 2, 2 to the first 2. and n is 2, 2 to the second 4, or when n is 3, the term is 3, 2 to the second 4, term is 4, 2 to the third 8, but it doesn't take care of the positive negative. So what if I did that? That would make my first term, when n is 1, I would get negative 2 to the 0th, that's 1. When n is 2, I get negative 2 to the first, that's negative 2. When n is 3, negative 2 to the second, that's positive 4, and we got it. Now, had these signs been negative, positive, negative, positive, and started out negative, in order to be in sync, I might just want to put an additional negative out in front of here, which does not distribute in. Exponents first, but we don't need that. The denominator, this is 3 to the first, 3 to the second, 3 to the third. We want 3 to the nth. And again, back of the book may have things look a little bit different than that. You might have to go through some algebra process to make certain that your answer matches the back of the book answer. Recursive definition. A recursive definition is a definition that bases a value in the sequence on a value or values that have preceded it. Yeah, we might say A1 is 28, and we might say AK is AK minus 1 minus 4, but the better way to say this is the first term is 28. Now watch this one. This ends up confusing people, but it shouldn't. Pay close attention and get questions asked on this if it doesn't make sense. Any term in our sequence is equal to the term right before it minus 4. So the 7th term would equal the 6th term minus 4. And the second term would equal, that's when k is 2, would equal the first term, which is 28, minus 4. The third term equals the term before it, minus 4. The fourth term equals the term before it, which is 20, minus 4. The fifth term equals the term before it, 16, minus 4. Okay, this might actually have a familiar feel to some of you. Here they give us A0. There's no magic in starting at 1. It's kind of normal, but you don't have to start at 1. The 0th term is 1. The first term is third. Any term out there is equal to the term that was 2 before it plus the term that was right before it. So A0 is 1. A1 is 3. A2, when k is 2, would be A0, 1, the term 2 before it, plus when k is 2, that's A1, the term that's 1 before it. Oh, I got it. A3 would be the term 2 before it, plus 1 before it. A4 would be the term 2 before it, or 4, plus the term 1 before it, or 7. And A5 would be the term that came 2 before it, A3, 7, plus the term that preceded it, A4, 11, 18. Sometimes this is easier if we just do it in a list. 1, 3, add these two, get 4, add these two, get 7, add these two, get 11, add these two, get 18, add those two, get 29, ... That is recursive for those of you who feel like maybe there's something familiar to this. Fibonacci sequence is recursive. Fibonacci sequence says 1, 1. No, thank you. You can come back. Bye.
What?
You guys can come back. Come back later. Thank you.
What?
Come back later, please. 1, 1, 2, 3, 5, 8, 11. This 8 came from adding those two before it. That's the Fibonacci sequence right there. Okay, sorry about that interruption. Let's continue on here. Write the first 5 terms of the sequence defined recursively. Oh, okay, well we can do this. This just says, much like what we were just doing right there, this just says we're going to go ahead and, and then what we're supposed to do is find a way to get to the nth term. If you sorry about that. Taking it back there a little bit. Try that again. Pretend that didn't just happen. In 59 through 62, we're going to do exactly what we were just doing. Then we'll come back and talk about the second part of this. So A1 is 6. This says a term, any term, now this could have been AK and AK minus 1, but this says, or you could read it this way, the next term equals the term we're at plus 2. Or a term equals the term before it plus 2. So this is just going to be 8, 10, 12, 14. And now we're supposed to write the nth term. Well, this is nice. Up 2, up 2, up 2, up 2. We start at 6. We start adding 2. How many times do I have to add 2 to get to 14? 4 times. But that's the 5th term. So it's 4 steps from the first term to the 5th term. How many steps to the nth? N minus 1. And we get 2n plus 4. Okay. Let's take a look. First term is 81. Any term equals 1/3 the term before it. Or to get to the next term, we take 1/3 times the term we're at. Times 1/3, 27. Times 1/3, 9. Times 1/3, 3. Times 1/3, 1. The nth term, we started 81. We started multiplying by 1/3. How many times did I multiply by 1/3 to get to the 5th term? 4 times, because it's 4 steps away. Steps. The number of steps is always 1 less than the number of terms. The number of steps from the first term to the 100th term is 99. You can get steps by subtracting the term numbers. How many steps do we need? N minus 1. By subtracting the first term number and the last term number anyway. Okay, we'll continue on here, and then I'm going to break this into 2 sections. I've got a few more minutes. In exercise 63 through 68, write the first 5 terms of the sequence using the table feature, and that's what we're going to do, and we've got this factorial in here. And I believe we have experience in factorials, but if we don't, 5 factorial means we start at 5 and we just start multiplying. And you may think, why in the world would we ever do that? And you're going to find out in this chapter there's lots of times real world problems we want to use factorials. So we're going to write the first 5 terms. And I get another quick interference here. I'll be right back. Okay, we write the first 5 terms. So this would be 1 on 2 factorial, not plus, comma, 1 on, the first term, when I put in 2 in here, I get 1 on 3 factorial, dot, 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 or comma, dot, comma, dot, comma. Anyway, let's go ahead and do this with calculator. So I'm going to go ahead into my y equals. I'm going to clear this. I'm going to set up a fraction, second y equals. I'm going to put 1, and I'm going to put that on parentheses x plus 1, close parentheses, and factorial. If you're on an 84 plus, I think you've got it here. I'm going to go alpha window. You can also go through, I'm going to show you another avenue to that. Let's clear out of that. You could also go through math probability and get it here. But alpha window is really convenient. And now I'm going to go back to my table. And there we have it. Our values are 1/2, as we could see. This would be 3 times 2, 6. 1/6. 1/24. 1 on 120. And I bet the next one is 1 on 720. 1 on 720. Started at 2. This is 1 times 2 times 3 times 4 times 5 times 6. That's a pattern of numbers you're going to see again, and we're going to hopefully recognize that as factorial. And 66, y equals. So I'm going to just change this to x to the 3rd, and that is on n plus 2 factorial. And we're going to go to our table. 1/3, 9/40ths, 4/45ths, 25 on 1008, and at some point we lose our fractions, but not yet. 3 on 560, and decimals there. If I didn't use, I believe if I didn't use this feature of my calculator right here, I believe we'd have decimal answers there, which maybe that's okay for some problems, but these are exact answers. Be very difficult to figure out the nth term based on this because they've got some fraction reducing going on here. Very, very difficult to do that. Okay, one time I'm going to do this. Find the sum, simplify the factorial expression. I'm going to wrap up this page on this, and then we'll have one more page of notes. 10 factorial, only one time I'm probably going to write all of this. This is 10 times 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1. Over 5 times 4 times 3 times 2 times 1 times 3 times 2 times 1. And what I normally do on this problem is I just go 10, 9, 8, 7, 6 and stop there because I know this 5 factorial, those factors will cancel those. And then I look for anything good that reduces, and I notice 2 times 3, 6 cancels this 6, and we end up with just 10 times 9 times 8 times 7. Second quit. 10 times 9 times 8 times 7. 50, 40. And you say, wow, that's strange. You know, why in the world would we ever have a problem like this? Well, I could come up with a story problem for you very, very quickly here. Here's a little preview, a little hint, little foreshadowing. I might use Fruit Loops to come up with a problem that would have an answer. Excuse me, an answer like that. But that's later in the chapter. All right, a little bit more abstract here. But 2n minus 2, I don't know what it is. I assume it's an integer. So the 2n minus 2 factorial would be 2n minus 2 times 1 less than that, 2n minus 3 times until we got down to multiplying by 1. Okay, that's what a factorial does. So this would be 2n times, what's 1 less than 2n? 2n minus 1, 1 less than that, 2n minus 2. I'm going to go one more. You may already see why. 2n minus 3. And how long do I do this? Until I get down to 1. The dots might make this hard, but I notice this. Cancels. Cancels. And all of these values right in here would match all of those values right in there. And I'm just left with 1 on 2n times 2n minus 1. They may distribute that in the back of the book. They might not. Okay, and then sigma notation, summation. This tells us we're basically going to climb the ladder from 3 to 5. We're going to let j equal 3, and then j equal 4, and then j equals 5. This number on top should always be, it theoretically could be equal to the number down here, but should pretty much always be bigger than the number down here. And this is not bad by hand, but it would be really bad if it was some enormous, if this was 3 to 500. We have to find all of those terms and then add them up along the way. So this becomes 1 on 3 plus 1 when I put 3 in. Then we add every following term plus 1 on, now I, is that I or j? Now it becomes 4. 1 on 4 plus 1 plus 1 on 5 plus 1, and then we're just responsible for adding those up. Let's see, that's 1 on 4 plus 1 on 5 plus 1 on 6, and least common denominator there. Can I do better than, we could go to calculator on this, but can I do better than 20? Can I do better than 30? It's just going to be 60 if we go to common denominator. So we could do that, but I'm going to go ahead and just enter this as 1 divided by 4 plus 1 divided by 5 plus 1 divided by 6. Enter, and math, fraction that guy. And we get 37 on 60. Now this one, I will see people try to, there's no k in here. But I still want to count my k's from 1 to 5. All there is here is a 4. So when k is 1, this is still 4. When k is 2 on its climb to 5, this is still 4. When k is 3, this is still 4. When k is 4, and when k is 5. And that, of course, equals 20. So here I get from 0 to 4, -2 to the 0th plus -2 to the 1st plus -2 to the 2nd plus -2 to the 3rd plus -2 to the 4th. And these are really tame. It would be a lot worse if that was a much, much bigger number. Let's see, -2 to the 0th, 1, plus -2 to the 1st, -2, plus -2 to the 2nd, 4, -2 to the 3rd, the negative survives, -8, and -2 to the 4th, 16. Positives, I've got 21. Negatives, I've got 16. Answer, I've got 5. So we've got some more to take a look at on our part 2 of this video. We've got most of it wrapped up. Here's our part 2. But here is the assignment, and you should be, with what you've seen there, in pretty good shape getting through, I would say, problem number 97. You've got some reference. There are some tough ones in there. A lot of it's just simple, straightforward mechanics, but when you have to find the nth term based on sequences, those can be pretty tricky. There'll be a lot of questions on those. I'm going to keep trying to have you battle through those. All right, let me know if I can be of any help.